Okay, hi everybody. We are going to walk through 711 today. This is 711/712 on your paper. We're just going to do the first section, 711 only, picking up right where we left off with logarithms and adding on to that. Let me zoom in. There we go. Okay, so we'll start just a quick recap of what we've covered so far in terms of what a logarithm is and how it relates to what we've already learned about. We know that logarithms are the inverse of exponential functions. So that's kind of the basic definition we know. Logarithms are the inverse of exponential functions. You will need a calculator today, so get one out if you don't have it. Come grab one of mine if you need it. Okay. Logarithmic equations can be written in exponential form, just like exponential relationships can be written in log form. So if we have something like this, log base b of x equals a, you should all know the relationship between bx and a at this point. So if this relationship is true, that means the exponential relationship b, the base of the log, is the same as the base of the exponent. B raised to the power of a equals x. So that's what we covered a lot in chapter 5. What do we know about the logarithm key on our calculator? So we've figured out there's a log button right here, and we know that as common log base 10. So that's what we know about our calculator button, is that it is a base of 10. What does the graph of log of x look like? And graphing form of the equation y equals log of x. We know the graph of log of x, we've graphed a few of these a couple weeks ago. They look like the reflection of the exponential relationship. So it's the reflection of y equals, specifically, if this is log base 10 of x, then its graph would look like the inverse of 10 raised to the x reflected over the line y equals x. And I'll draw a really quick. So if this is this is 10 raised to the x, then log base 10 of x would look like that. Okay, and lastly, this is what we ended chapter 5 with, was graphing logarithmic functions. In graphing form, we saw the same parameters a, h, and k. So we had the stretch factor times the log of x minus h plus k. So this is just a very quick recap of what we've done up to this point. Oops, sorry. Okay. This is a recap of what we've done up to this point, and now we're going to kind of add on to that and see how we can use logarithms to solve exponential equations. So we haven't used them yet. We've just been practicing understanding what they are, and now we will actually apply what they can do for us in solving equations. Before we do that, I want you to think about these 4 situations, and I'll demonstrate them on my calculator if we need to. So first of all, we just want to know, think about this. Does log base 5 of 25 have the same value as log base 25 of 5? So can we just flip-flop those values? So think about that for a second. Log base 5 of 25. This is going to equal whatever power of 5 you need to get 25. So we know that 5 squared is 25. And then is that the same as whatever power of 25 you need to get to 5? The answer to that is no, those are definitely not the same. What power of 25 results in 5? Well, we know the square root of 25 equals 5. And square roots can be rewritten as powers. So that would be 25 to the 1/2. So we know these are not equal. We cannot just flip-flop these two numbers, the base with what's in the log. So I think all of you probably intuitively understand that already. This next one we want to look at and think about is if I'm taking the log of x squared is that the same as taking the log of x by itself and then squaring it? So this I wouldn't necessarily expect you guys to know, but I can graph both of these and we can just look at the graph. I can look at the graph if I make that a y equals and that a y equals. If those two graphs are identical, then it's true. So let's just test it. So we want to graph log of x squared. And then on a separate line, I am going to do parenthesis log of x and parenthesis and then squared. So I'm squaring x first in the top, then taking the log, and then I'm squaring then I'm taking the log of x and squaring that. So if I look at my standard window, here is the log of x squared, and then the log of x and then squared. So we can see those are two completely different graphs. So it is not the same. So this is not true. You cannot change what's being squared to being the outside versus the inside. So that's not true. Let's look at this other situation. Is log of 7 raised to the x, so that's inside the log, the same as x times log of 7? So in other words, can this exponent, instead of being at the exponent of 7, can it be brought down here and multiplied by log of 7? So let's try both of those. So the log of 7 raised to the x, is that the same as x times the log of 7? What do you think will happen? Okay, go back to my standard viewing window. Here is the log of 7x. Ends up just being linear because it just equals powers of 10 that equal. Oh, and then we see the second graph come on top of that. I don't know if you saw that. It changed from blue to red, which, oops, that's my pen, which means these two things have the same graph. That is strange, but really important. Yes, those generated the exact same graph, and that is going to come in handy to us. Okay, let's check this one last situation. Is log of 2x the same as log base 2 of x? So in other words, can we take one of the factors inside of here and just change the base from base 10 to base 2? What do you guys think? This one, I'm not going to show you the graph, but I just want you guys to think of it. Log base 10 of 2x, does that equal log base 2 of x? So 10 to some power equals 10 to some power equals 2x. Is it going to be the same as the power of 2 that equals 1x? This is not going to be true ever. So we see these situations kind of just asking if they are the same. We saw 3 no's, but this one right here is going to be really significant in how you guys use logarithms. Let's test it with a couple of others. So if it's true that we could do log of 7 to the x, and that equaled the same as x times log of 7. So what happened? This exponent is now in front of the log. So let's try that with a couple of other values. So if that's true, shouldn't it be the same if we just changed it? What if we did log of 2 to the x? Is that going to be the same as x times, if I follow the pattern, it should be the same as x times the log of 2. Let's test that. So log of 2 raised to the x, is that the same as, if we bring that x down front, x times log 2. And then I'll go to my standard viewing window again. Here's the first one, log of 2 raised to the x. And then we should see the second one, x times log of 2, fill in right on top of that, the same exact graph. So we see this consistency and same line, same function when we take an exponent inside of a logarithm and bring it down front. This is called the power property of logarithms. And just like we have already reviewed and talked about how logarithms are the inverses of exponents, logarithms undo exponents. So when you have the log of something raised to an exponent, this log can undo the exponential piece and turn it into multiplication. That's going to give us the tool that we have been missing to solve equations like this, where, like in this next example, where our variable is in the exponent. Now we can undo that exponential operation using logarithms, since logarithms undo exponents. So the official power property of logarithms is if you've got the log, any base, it doesn't matter what the base, I'm just doing base 10 or common log, of some base m raised to the power of n. This will always be equal to the same thing if we bring that exponent down front and multiply, whoops, that should say n times the log of m. Log of m raised to the n equals n times log of n. This is the power property of logarithms. So useful, so important. Put a bubble, stars, whatever you need to remind yourself. This is a key factor in how we're going to solve exponential equations. Before we just figured out that power property, if I wanted to solve this equation, basically you guys would have to resort to guessing and checking. Guessing 1.04 raised to what power is 2? So you would just try a bunch of powers. 1.04 raised to the what is going to get me to 5, or to get me to 2. So instead of this, guessing and getting as close as we can just use the inverse of exponential relationships, which is logarithms, to undo this. So if I want to get that exponent out of the exponent, all I need to do is apply a logarithm to both sides. Logarithms are not numbers, they're entire functions. So I can apply a function log of x to this side as long as I apply the same function to this side. I'm going to pause and just remind you of other ways we've seen this. You don't even need to write this down. I just want you to think of it. When we're solving equations like this, if I say solve for x and you take the square root of both sides, you are applying the inverse functions, the inverse of squaring, which is square root, to both sides. You're not multiplying both sides by square root. Square root isn't a numerical value, it's a function. Same with logarithms. So we are applying the log function to both sides, which is going to undo this exponent. It's going to turn it into multiplication. So now we know we have a new equation, x times the log of 1.04. It's no longer being raised to the x because the x is out front, equals log of 2. Now, if I want to solve for x, right now x is just being multiplied by log of 1.04. So to get x by itself, we're going to divide both sides by log of 1.04. So on the left, x is now by itself. Then we just need to evaluate log of 2 divided by log of 1.04. So that's where you'll need a calculator, and you type it in exactly as you see it. So log of 2 end parentheses divided by log of 1.04. So you're just typing it in exactly like we see it. Make sure you close the parenthesis here after this 2, otherwise you'll get the wrong answer. Hit enter. There's our answer, 17.67. About 17.67. And then if you're unsure, and since this is a new process, a new use of logarithms, you could always just go back to the original problem. Supposedly 1.04 raised to this number, 17.67, is 2. Now we rounded, it's a decimal approximation, but it's a quick check. We can actually just plug our answer back in for x here. So 17.67, 1.04 raised to the 17.67 It's not going to be exactly 2, but it's really close because we did round it. But that's a quick way to check it. Just plug your answer back in as the exponent in your original equation and make sure that that makes sense. So again, now we have this awesome tool to solve exponential functions that we just haven't been able to before. Here's another example. We will round to 3 decimal places moving on. Exponential and logarithmic relationships change so much so fast that it's just the more precise you can be with rounding, the better. So we'll go out to 3 decimal places. Okay, solving this equation, we need to stop and recognize that the variable we are solving for is stuck in the exponent. We need to undo that. We need to get the exponent out of the exponent, and that's going to be with a logarithm. So in order to do that, we need to apply the log function to both sides. So I'm applying log to the left, which means I can do log on the right, 2.25 to the x. Then we apply that power property, the whole idea here. And this exponent can come down in front of the log of 2.25. So then we have log of 5 equals x times log of 2.25. We are no longer solving for something stuck in an exponent. Now it's just being multiplied by log of 2.25. So we can divide by log of 2.25, both sides. Cancels out on the right. And then we've got x by itself. We just need to evaluate this, which is where our calculator comes in handy. So we'll do the same thing, log of 5, close your parentheses there, divided by log of 2.25, and we get about 1.985. Again, oops, 1.985. You've got a quick way to check this right here. Just plug it right back in. So when I do 2.25 raised to the 1.985, again, we rounded, but it should be pretty close to 5.001. Okay, why don't you guys try B on your own? I'm just going to stop talking for a second. I want you guys to try this one. Okay. Hopefully you guys are at least most of the way through this problem. Apply log to both sides. X comes down, divide both sides by log of 3.5. And you should end up with what? Log of 10 divided by log of 3.5, about 1.838. Okay. All right, so that is how we apply a logarithmic function to both sides of an equation to undo that exponent. I have just a few more examples, and then I'm going to have you guys work on a worksheet just covering this. I want to talk about this next one on the next page, example C. So when we are undoing a function, it's important that we isolate that function first. I'm going to show you a completely different example. You don't even need to write it down. I just want you to look and pay attention. Similar to that same one I had on the other page where I had x squared equals 100. Well, what if, oh, that is bright. Okay, that's better. Okay. What if there was something else out here attached to this, like a 5? and I said solve for x. The first thing you would have to do before you take the square root of both sides is get this x squared by itself. So you'd have to divide both sides by 5. So then you would have x squared equals 20. Then you can take the square root of both sides, which is the inverse of x squared. So just like that, when you're solving exponential equations, before you take the log of both sides, you need to isolate the exponential piece. So we want 8 raised to the x by itself before we apply log to both sides. I'm going to show you one other example. It might not be multiplication, but if we had like x squared plus 15 equals 100, and I said solve for x, you would not take the square root of both sides right away. The first thing you would do is subtract 15, get x squared by itself, then you can take the square root of both sides. Same thing with logarithms. So when we're solving this, we see our exponent is where the variable is, and we need to undo that, but not until this exponential piece is by itself. So first we divide both sides by 2. And then we've got 8 raised to the x equals 64. And now we can take the log of both sides. So we can take the log of this side, and you guys will probably start doing this. You will probably, if you haven't already, start bringing that out in front all in one step, which is totally fine. I've been showing the process step by step by step just to make sure you guys are following what's happening here. But just don't forget, if I apply a log to that side, I need to apply log to this side as well, 64. Okay, and then the last step here is just divide by log of 8. So x would equal log of 64 divided by log of 8. So then we can just type that in here. Log of 64 divided by log of 8, and we get 2. Some of you may have already figured out the answer was 2 right here, because you saw 8 to the x equals 64. We know that 8 times 8 is 64. So you may have gotten to this point and said, okay, I don't really need to apply a log to both sides because I know that x has to equal 2. That's totally fine. Just because we're solving exponential equations doesn't necessarily mean you will rely on logs every single time. Especially like in cases like this, you won't necessarily need to. But if you do, if you go straight to the log, you can still get there using logarithms. All right, this other example here, think about, I want you to really look closely at example C and then again at example D and see what you notice changing from one equation to the other. We have 2 times 8 raised to the x equals 128. Over here, we have 2 times x raised to the 8th equals 128. These are two completely different problems. The only change is that instead of 8 raised to the x, I've swapped it, and now my base is x and my power is 8. This is not an exponential equation. My variable is not an exponent. My variable is the base. We do not need logarithms when we are not solving exponential equations. So just because you see a base raised to a power doesn't necessarily mean you need to jump in with a logarithm, because we use logs to undo exponents when we're solving for that variable that has the exponent. This we can solve using skills you guys already have. Just like I showed you up here, before I took the square root of both sides, I needed to get rid of this plus 15 or divide by 5. Same idea here. Let's get rid of this 2 first, and we'll just divide both sides by 2, just like we started over here. But then we end up with x raised to the 8th equals 64. Now, to undo raising something to the 8th power, there's 2 ways you can think about it. We need to take the 8th root, or you can also think about it as what power can I raise this to that will undo being raised to the 8th? And the 8th root can also be taken by raising it to the 1/8 power. So it's up to you guys. Those are the same things. 8th root and raising it to the 1/8 power is the same. But that's going to undo x being raised to the 8th. And we'll just do 64 raised to the 1/8, like that, which is 1.682. About 1.682. You could have done 8th root if you have a graphing calculator and you hit the math key and then you arrow down to x root. If you select that, you can tell it to take the 8th root of 64, and it'll give you the same output. Okay. I said just a couple more examples, but I actually secretly have one more example that will help you on this worksheet. It's just going to be off of here to the side. Example E, one quick one, kind of summarizing all of what we've been talking about in one problem that's a little more involved. So if I have 3 times 5 raised to the x minus 4 equals 75. So write this one down. We have a lot going on here. I wanted one that had more than just a base raised to a power. So we have 3 times 5 raised to the x minus 4 equals 75. First, we just take a step back and look, what am I solving for and where is it? I'm solving for x. It is stuck in the exponent, just like it was in the exponent up here. That means we're going to use logs eventually, not right away. I cannot take the log of both sides until I isolate that exponential piece. So I have to undo these other 2 operations that are happening. The first thing we need to undo is get rid of this minus 4 by adding 4 over. So then that'll leave us with 3 times 5 raised to the x equals, add 4 to 75, and we've got 79. Still not ready to take the log of both sides. First divide by 3. Now, here is where I want you to keep the fraction. Don't round this decimal yet. The earlier you round in a problem like this, the less accurate your answer is going to be, especially with exponential relationships. So 79 divided by 3, that is not a terminating fraction. It repeats forever. Do not round it yet. So just leave it as a fraction, 79 thirds. Now we're ready to undo 5 being raised to the x by taking the log of both sides. So I can take the log of this side as long as I take the log. I'm kind of just squeezing in, taking the log of both sides. When we take the log of 5 raised to the x comes down. And we end up with x times log of 5 equals the log of, again, just leave it as the fraction, 79 thirds. Then we can finally solve for x by dividing by log 5. It's going to be log of, again, leave it, 79 thirds divided by log of 5. So this very last step, that's where we will round. So to type that in, just make sure you're careful with your parentheses here. So we would have log of 79 thirds, end parentheses, divided by log of 5, end parentheses. And then we get our solution about 2.032. Okay. I wanted to show you that because there are a couple on the worksheet that you guys are going to work on now. So you will pick this worksheet up before you grab it. I just want you to look really fast and make sure you guys are, let me zoom out, paying attention to the directions. These 2 problems, these should look familiar from the practice we've been doing in class with these. These are exponential equations. We know that because our variable x is stuck in the exponent in both of them. Just because you're solving exponential equations doesn't necessarily mean you will rely on logarithms. In these cases, you can just rewrite this larger number as 7 raised to a power. And same with this. We've got 216 raised to a power equals 6 raised to a power. We can break down 216 as 6 raised to some power raised to the 3x and then multiply those. So these should look familiar. I don't feel like I need to get too far into these. So work through these first without using logarithms and property. And then down here, this is where you will practice applying the log to both sides to solve those exponential equations. When you're done with this, check your work with my key, and then you can turn this in and then work on your closures for the rest of class. Reminder that the chapter 5 closure will be due Wednesday, and that is when your test will be. Okay, that's it. Okay, how do I stop? Okay, bye.